Okay, hi everybody. Sorry I'm gone. Today you're going to learn about even and odd functions. So here's an introductory Oh, and please take notes. Please take notes on this. To launch us into the topic, here's an introductory problem. So let's pretend I asked you to solve for x. You may not remember an important fact about cosine that would then make this very difficult or impossible to solve. Here's the fact that you might not remember. Cosine x is actually equal to negative cosine x, and there's two ways that you can see that this is true. If you think about the meaning of cosine on the unit circle, cosine x is the angle, the positive angle x wrapped this direction, and cosine is giving you the x coordinate. Negative x would be that same angle, but in the opposite direction, and you can see that they would have the same x value, no matter what direction the angle was going. If you imagine the graph of cosine x, you could have an x value out this way, and the cosine would have a certain value, or you could imagine negative x, which would be the reflection around the y-axis, and you'd have the same value. Because the cosine function is symmetric, it has a horizontal reflection symmetry around the y-axis. So the reason that's important is because once you know that it has this symmetry, so those are the same, you can rewrite this so that this is equal to 2 cosine x. So then you'd have cosine x is 1, and then you'd know that x is any multiple at all of 2 pi, any integer multiple of 2 pi. So like that. Okay, so cosine x is an example of what we call an even function. Even functions are functions that have this reflectional symmetry across the y-axis. So we're going to define them sort of geometrically and algebraically. Geometrically, they have a reflection symmetry around the y-axis. You can express that same idea algebraically by saying that f of x equals f of the opposite of x. And the way this makes sense is f of x is your untransformed function. And we're saying that your untransformed function is the same as your function with this transformation applied. And this is a horizontal reflection. So any equation f for which this equation is true, what that means is that the untransformed one is the same as the transformed one. In other words, if you take the graph and you apply the transformation, you end up with the original graph. Take a minute and see if you can write down a couple other examples of even functions. And it might be nice to even see if you could come up with a function whose graph you don't immediately know what it looks like, but you could for sure know that it was even. So pause the video and think for a minute. Some common families that are even would be cosine x, x squared would have that same symmetry, or absolute value x, and there's lots more. What if we wrote something down like this, x to the 6th minus x to the 4th plus 1? Is that even? A great way to test would be to see if this function satisfies this equation. So let's try it out. If I plug in f of x on the left, I've got x to the 6th minus x to the 4th plus 1. And the question is that the same as if I substitute in negative x? So in that case, I'd have negative x to the 6th minus negative x to the 4th plus 1. Well, when I take these negatives and I raise them to an even power, all of the negative signs cancel each other. So the answer is yes, that is the same. This ends up as being x to the 6th minus x to the 4th plus 1. So because they ended up the same algebraically, that's confirmation that whatever this function looks like, it's got to be an even function, so it has to have that reflectional symmetry. Okay, everybody, sorry, I got interrupted, and now I forgot what I just said a second ago. Anyway, odd functions are a different type of symmetry. So an example of an odd function would be x cubed, and the type of symmetry they exhibit is a 180-degree rotation about the origin. So let's write that down. So an odd function geometrically is a 180-degree rotational symmetry around the origin. So what that means is the point 2, 8 would get rotated around to -2, -8. Algebraically, that's saying that the original untransformed function is the same as the opposite of f of the opposite of x. And you should think about what this means in terms of transformations for a minute. It means the untransformed one is the same as one that has been horizontally reflected and also vertically reflected. And you can convince yourself for a minute that that is the same thing as a 180-degree rotation about the symmetry. 180-degree rotation around the origin. So if you imagine reflecting 2, 8 first horizontally, you'll get -2, 8. And then you reflect it vertically, and you'd get -2, -8. So just like before, go ahead and think of some examples of other odd functions. Maybe a more complicated function that you think is odd. So here are a couple of other common odd functions, x to the 5th, or any odd polynomial like this. Sine of x. You might immediately have some questions. So like for numbers or for integers, all integers have to be either even or odd, but they can't be both. So spend a minute and think. If I make up any function f of x, does it have to be even or odd? Could it be both? Could it be neither? Think about that for a minute and a half. I'm going to pause the video. Hopefully you could pretty quickly come up with an example of a function that's neither even nor odd. So for example, log of x doesn't have this rotational symmetry, and it also doesn't have the horizontal reflection symmetry. So it's neither even nor odd. The only function that I can think of, which is both, is the horizontal line y equals 0. That one you can imagine rotating the horizontal line 180 degrees, and it's the same. You can also imagine reflecting it, and it's the same. Whether or not this is the only function that's both is something that you would need to figure out how to prove if you really wanted to answer this question definitively. But I don't care that much. I just wanted you to think a little bit about this. So let's say that you have a function like this, where you don't know what the graph looks like. You can use these descriptions of the symmetries that even and odd functions have in order to test to see, does this unknown function have that kind of symmetry? You are going to need to know these eventually, but I think they're not that hard to memorize if you remember geometrically, even functions have the reflection and odd functions have the rotation. And then you just remember that you're describing those geometric symmetries using transformational algebra like this. So if you want to, you can pause the video and give it a little shot. I'm going to solve it right now. So let's test to see whether it's even. So if it's even, I know that this should work out to be true. Oops. So on the left-hand side, I've got e to the x plus e to the negative x over 2. And on the right-hand side, I want to know, is that the same as what happens if I substitute in negative x? So that gives me e to the negative x plus e to the negative x over 2. And this seems like it's going to work. Here I've got e to the negative x, and then here the opposite of x is just x. And now, because a plus b is the same thing as b plus a, I know that those two sides are equal. Therefore, I've shown that this function's even, which means that whatever the graph looks like, I know it has this horizontal reflection symmetry. So what you're about to do is try and explore and predict and prove some properties of even and odd functions. So choose one of these questions to investigate below and fill in the blanks to make it specific, and then predict what the answer is. And you can predict based on experiments with even and odd functions that you know about, or so you can use Desmos if you want, or you could try to jump directly to a generalization. But make some type of prediction and then try and prove the result algebraically using a test. So if you want to, like, maybe let's just do a quick example. So let's say the sum of two even functions is always, I don't know what. So what's that going to look like? Earlier on, I had this prediction, or I had this function where I'm combining a couple of functions that I know are even, and the result ended up even. So I'm going to guess that if I add together two even functions, the result is probably even. So if that's my guess, here's one way that you could prove that that was true in general. Let's say f and g let f and g both be even functions. The question is f plus g even? So prove f plus g is even. We could define a new function h, that's the sum of our two even functions. And so the question is it true that h satisfies the test for being even? Well, let's just expand both sides. So h is the same thing as f plus g. And now this side is the same thing as f of opposite x plus f of opposite, g of opposite x, because I took the definition of h of x and I substituted in negative x. Because I know that f and g are both even functions, they also satisfy the definition of an even function. So this is the same as f of x, this is the same as g of x, and that's been a very easy proof. If that seemed very abstract to you, it would make a lot more sense if you imagined this with a specific example. So let's say this is x squared and x to the fourth. You know that both of those are even functions. So the question is this true? And it's very immediately clear that it is, because this is negative x squared, and this is negative x to the fourth, and you know that in both cases, the negative signs are going to cancel each other, and you end up with the same thing. So that's all that's happening over here. It's just that we're using the fact that we know it's even to assert that those two things are equal, because that's the property of being even. So, to be clear, this is not a proof. This is an example of two even functions that combine to be even. But it gives you the idea, and then over here, this is a proof, because here we're not assuming anything at all about what f and g look like, except for the fact that they're even functions. So that's the kind of thing that you're going to try and do for the rest of the block until your practice quiz. Good luck.